What if I told you that humanity spent nearly $1 billion to look at something for just 13 minutes? And that same 13 minutes rewrote everything we thought we knew about the solar system's edge. But here's the real question. If it took us 85 years to barely touch Pluto, how long would it take to reach the nearest star? The answer will shock you. Picture this. A world so remote that sunlight, racing at 300,000 kilometers per second, takes over 5 hours just to arrive. This is Pluto, a mysterious ice ball drifting through the cosmic darkness, more than 6 billion kilometers from home. For decades, it existed only in our calculations and imaginations, a mathematical ghost at the solar system's edge. July 14, 2015 changed everything. For the first time in human history, we glimpsed Pluto's true face. But here's the catch: our only visitor, New Horizons, didn't stop. It couldn't stop. At nearly 50,000 kilometers per hour, it screamed past in mere hours, cameras clicking frantically, then vanished into the void beyond. Why would we invest nearly $1 billion and a decade of travel for just a fleeting glance? The answer reveals something profound about the physics of distance, the economics of exploration, and the staggering difficulty of reaching and actually stopping at the edge of our cosmic neighborhood. Rewind to 1964. A young engineer named Gary Flandreau was running calculations at NASA's Jet Propulsion Laboratory when he stumbled upon something extraordinary. The outer planets Jupiter, Saturn, Uranus, and Neptune were slowly aligning into a configuration that occurs once every 176 years. This cosmic coincidence would create a gravitational highway, allowing a single spacecraft to visit multiple worlds by stealing momentum from each planet it passed. The opportunity window? Just 2 years, between 1976 and 1978. Miss it, and our grandchildren's grandchildren would be the next generation to see such an alignment. NASA's response was the Grand Tour project, an audacious plan featuring 4 spacecraft called TOPS thermoelectric outer planet spacecraft. The vision was breathtaking. One probe would visit Jupiter, Saturn, and Pluto, arriving at the ice dwarf by 1985 or 1986. Another would explore Jupiter, Uranus, and Neptune. But dreams collide with budgets. The price tag was astronomical. And in the early 1970s, with public enthusiasm for space waning after Apollo, Congress balked. The Grand Tour died before launch. In its place came a compromise: the Voyager program, cheaper and more modest, but brilliant nonetheless. Here's where history pivoted on a single decision. After Voyager 1E's Saturn encounter, mission planners faced a choice: redirect toward Pluto, arriving in spring 1986, or dive close to Titan, Saturn's enigmatic moon with its thick atmosphere. They chose Titan. One decision, one moon. And Pluto would wait another 29 years for visitors. Understanding why we only flew past Pluto requires grasping a counterintuitive truth about space travel. Getting there fast and stopping there are fundamentally opposite goals. Gravity assists are spectacular for building speed. Each planetary flyby is like a cosmic slingshot, stealing orbital energy and flinging you faster toward your destination. New Horizons gained 4,230 meters per second, over 15,000 kilometers per hour from its Jupiter flyby alone. This technique turns weeks into years of chemical rocket burn, making distant missions possible. But here's the brutal paradox. Every kilometer per hour you gain through gravity assists must somehow be shed if you want to enter orbit. New Horizons approached Pluto at 49,600 kilometers per hour relative to the dwarf planet. To break into orbit would require a propulsion system capable of canceling nearly all that velocity. The rocket equation is merciless. To slow down requires fuel, but fuel has mass. And accelerating that fuel mass from Earth requires even more fuel. The mathematics spiral exponentially. For New Horizons to carry enough propellant to orbit Pluto, it would have needed to be perhaps 5 to 10 times heavier at launch, demanding a larger, more expensive rocket, heavier solar panels or nuclear generators, and costs spiraling into the billions. The alternative? Nuclear electric propulsion systems generating steady thrust over years, or arriving more slowly via different trajectories that sacrifice gravity assists. Both options translate into decades of additional travel time or technologies that, in 2006, existed only on drawing boards. So mission designers made the pragmatic choice: make the encounter count. Pack every possible instrument into those crucial hours, then continue into the Kuiper Belt. One shot, no second chances. The 1980s and 1990 seconds became Pluto's dark age, a frustrating cycle of proposals, enthusiasm, and cancellation. Each mission concept fought against the same enemies: vast distance, limited power, political skepticism, and the perception that Pluto was scientifically inferior to destinations like Jupiter's Europa or Saturn's Titan. Consider Pluto 350, proposed just 2 months after Voyager 2E's 1989 Neptune encounter. At 350 kilograms, it would carry just 4 instruments: a camera, an ultraviolet spectrometer, a radio package, and a plasma detector. The science community's response? Too risky, too lightweight. The Voyagers weighed 800 kilograms. Surely anything smaller would fail. The paradox deepened. Make the spacecraft heavier and more capable, and costs explode. Keep it light and affordable, and critics question its reliability. Pluto missions became trapped in an impossible middle ground. Meanwhile, urgency was mounting. Pluto reached perihelion, its closest approach to the Sun, in 1989. As it receded on its 248-year orbital journey, its tenuous nitrogen atmosphere was freezing and collapsing onto the surface. Scientists feared waiting another decade might mean studying a world fundamentally different from its active state. The 1990s brought increasingly desperate efficiency drives. Pluto fast flyby aimed for under 150 kilograms, impossibly small by earlier standards. It evolved into Pluto Express, then Pluto Kuiper Express, each iteration shaving mass and cost while trying to preserve scientific capability. All were cancelled. Budget cuts, competing priorities, and skepticism about visiting what many increasingly saw as just another Kuiper Belt object rather than a real planet. By 2000, the planetary science community faced an existential crisis regarding Pluto. Launch windows that could use Jupiter for gravity assists were closing. Miss the 2001 to 2006 window, and the next favorable alignment wouldn't come until the 2020s. Pluto's atmosphere might be completely frozen by then. NASA took an unprecedented gamble, an open competition. Rather than choosing a mission concept internally, they invited teams to compete for funding under the newly created New Frontiers program, more expensive than Discovery missions, but cheaper than flagship missions like Cassini. On February 5, 2001, the winner emerged: New Horizons, led by the determined Alan Stern, who had been championing Pluto missions since the late 1980s. The design philosophy was radical minimalism. Every gram counted. The spacecraft's distinctive triangular shape came from literally cutting corners off a conventional design to save mass. The antenna diameter shrank from 3 meters to 2.1 meters. The original for science packages were consolidated and miniaturized into 7 instruments, weighing just 30 kilograms total. The final spacecraft, 478 kilograms, smaller than a grand piano. Powered by a plutonium-238 radioisotope thermoelectric generator producing just 200 watts less electricity than a modern gaming computer consumes. The total mission cost, $646 million in 2024 dollars. Expensive, yes, but a bargain compared to the multi-billion-dollar alternatives proposed and rejected over the previous 2 decades. Launch came on January 19, 2006, atop an Atlas V rocket with 5 solid rocket boosters, the most powerful configuration ever used for a planetary mission at that time. New Horizons left Earth faster than any previous spacecraft, crossing the Moon's orbit in just 9 hours. The Jupiter flyby in February 2007 was both scientifically productive and practically essential, adding that crucial 4,230 meters per second of velocity. Then came 8 years of hibernation, crossing the vast emptiness beyond the gas giants, occasionally waking to check systems and test instruments. July 14, 2015. After 3.26 billion miles and 9.5 years of flight, New Horizons reached Pluto. The closest approach lasted just 13 minutes, the span of time it takes you to make a cup of coffee and check your phone. In that brief window, traveling at 49,600 kilometers per hour, New Horizons had to execute perfectly. There would be no second chances, no course corrections, no do-overs. What we discovered shattered every expectation. Pluto wasn't a dead, crater-pocked iceball frozen since the solar system's formation. Instead, cameras revealed a world of staggering geological complexity. The famous HART, officially named Tombow Regio, showed regions of smooth plains made of nitrogen ice, completely devoid of impact craters. This meant something extraordinary: geological activity within the last 100 million years, perhaps even continuing today. Mountain ranges composed of water ice rock hard at Pluto's 230°C. Temperatures rise up to 3,500 meters high. Glaciers of nitrogen ice flow across the surface. Complex patterns suggest convection currents in underground oceans of ammonia-laced water. The atmosphere, though tenuous, proved more extensive than predicted, with haze layers extending 200 kilometers above the surface. And Charon, Pluto's largest moon, revealed its own surprises: a dark polar cap, likely composed of organic molecules called tholins, created when methane escapes Pluto, gets captured by Charon's weak gravity, and is chemically transformed by sunlight. The data revealed a world far more dynamic and geologically alive than any icy body had the right to be at such extreme distance from the sun. The heat source driving this activity remains mysterious, perhaps radioactive decay in Pluto's core, or tidal heating from its gravitational dance with Charon. New Horizons didn't just visit Pluto. It revolutionized our understanding of dwarf planets, Kuiper belt objects, and the possibilities for geological activity in the frozen outer solar system. Then, having completed its primary mission in those 13 minutes, New Horizons continued outward, eventually visiting another Kuiper belt object, Arrokoth, in 2019, becoming humanity's most distant planetary encounter ever achieved. If reaching Pluto took extraordinary effort, consider this: visiting the nearest star system is incomparably harder. Proxima Centauri lies 4.24 light-years away, roughly 40 trillion kilometers. To put that in perspective, if Earth were a grain of sand in New York City, Pluto would be in Philadelphia. Proxima Centauri would be in Tokyo. Voyager 1, humanity's fastest and most distant spacecraft, traveling at 17.4 kilometers per second, would take 76,000 years to reach Proxima if it were heading that direction, which it isn't. For a mission completing within a human lifetime, say 50 to 130 years, we'd need velocities of 10,000 to 25,000 kilometers per second. That's 3-8 the speed of light. Chemical rockets, absurdly impractical. To reach even 1% of light speed with chemical propulsion would require propellant mass 1026 times the payload mass. That's a fuel tank with more mass than Earth itself. For perspective, the entire observable universe doesn't contain enough rocket fuel to make this work. Nuclear propulsion? Project Orion proposed riding nuclear explosions, literally detonating bombs behind a massive shock plate. For Proxima, you'd need 300,000 fusion detonations, a spacecraft mass of 400,000 tons, and a 100-meter pusher plate. Travel time, 150 years. And you'd still only achieve a flyby. Solar sails offer elegance, ultra-lightweight reflective surfaces pushed by photon pressure. But even massive, perfectly engineered sails would take 1,000 to 2,000 years reaching Proxima. Advanced concepts like Vossimer plasma engines or nuclear electric propulsion are revolutionary for Mars missions, potentially cutting transit times from 18 months to 39 days. But for interstellar distances, still, thousands of years. The physics are unforgiving. The distances are almost incomprehensible. And yet, there's one approach that might work within our lifetimes. The most promising proposal for visiting Proxima Centauri doesn't involve larger rockets or more powerful engines. Instead, it embraces radical miniaturization and a completely different acceleration paradigm. Breakthrough Starshot, funded by entrepreneur Yuri Milner and backed by scientists including Stephen Hawking before his death, envisions thousands of Starships spacecraft the size of postage stamps, weighing just a few grams each, attached to ultra-lightweight reflective sails measuring 4 meters square. The propulsion system, Earth-based. A massive phased array of lasers, either in high orbit or at Lagrange points, would generate approximately 25 gigawatts of power, roughly equivalent to 20 nuclear power plants working simultaneously. These lasers would focus their combined beams onto each sail for just a few minutes. In that brief firing window, the Starship would experience accelerations of approximately 100 km/s, about 10,000 times Earth's gravity. Obviously, no human could survive such forces, but microelectronics can be engineered to withstand them. The result? Final velocities reaching 15-20 the speed of light, between 45,000 and 60,000 kilometers per second. At that speed, the journey to Proxima Centauri would take 20 to 30 years, with an additional 4.24 years for radio signals carrying data to return to Earth. Why send thousands? Redundancy. The interstellar medium isn't empty, it contains dust grains, hydrogen atoms, and debris. At 20% light speed, even a collision with a grain of sand carries enough kinetic energy to destroy the craft. By launching thousands of Starships in a swarm, enough should survive the journey to return meaningful data. The science payload must be radically miniaturized. Cameras with optics measuring millimeters across, spectrometers built on single silicon chips, communication systems using tiny lasers powered by equally tiny plutonium power sources. This isn't science fiction, the engineering is theoretically sound, but enormous challenges remain. Laser systems maintaining precision over light years, materials science for sails that can reflect 99.999% of incoming light without absorbing heat, electronics surviving both the acceleration and decades of cosmic ray bombardment, and ground stations capable of receiving incredibly faint signals from probes light years away. Breakthrough Starshot's leadership believes that with adequate funding, billions, not trillions, the technology could be ready for launch within 30 to 50 years. Imagine, a spacecraft launched in 2060 could return the first photographs of Proxima Centauri B, a potentially habitable exoplanet, by 2110, within the lifetime of children born today. Here's what connects Pluto and Proxima. Both seemed impossible until someone refused to accept impossibility. New Horizons succeeded because Alan Stern and his team spent 17 years refusing to give up, optimizing every engineering detail, fighting for funding through 5 canceled missions, and finally threading the political and technical needle to launch in the last available window. Pluto taught us that too far is temporary, that dwarf planets can be geologically alive, that the outer solar system holds wonders we never imagined, and that with sufficient ingenuity and determination, even destinations requiring decades of flight become reachable. Proxima represents the next horizon, the transition from interplanetary to interstellar civilization. The engineering challenges are exponentially greater, but the principles remain. Think smaller, think lighter, use every advantage physics offers, and accept that transformative projects require generational commitment. If Starshot launches in 2060 and returns data in 2110, the scientists who designed it won't live to see success. The engineers who built the laser arrays might be retired or gone, but their children and grandchildren would inherit humanity's first glimpse of another star's planetary system, actual photographs, not just telescope dots confirming whether worlds beyond our solar system could harbor environments suitable for life. Every impossible mission completed makes the next impossible mission more possible. The Voyagers proved we could reach the outer planets. New Horizons proved we could reach Pluto. Future missions to Proxima will prove we can bridge the stars. The universe is under no obligation to make exploration easy, but it does reward creativity, persistence, and the willingness to think differently. When conventional rockets fail, we turn to gravity assists. When gravity assists aren't enough, we consider nuclear propulsion. When even that falls short, we imagine riding beams of laser light. Carl Sagan once wrote, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Each mission we launch extends that self-awareness a little farther. Pluto showed us we could reach the edge of our solar system and find beauty in the cold darkness. Proxima will show us whether we can transcend that edge entirely, whether the gulf between stars is a barrier or merely the next ocean to cross. The journey itself changes us. The technologies developed for space exploration, miniaturized electronics, advanced materials, precision optics, artificial intelligence transform life on Earth. The perspective of seeing our world from space shifts how we understand our place in the cosmos. And the commitment to multi-generational projects teaches us to think beyond our individual lifetimes. If humanity survives long enough, historians thousands of years hence will look back at this era, the 21st and 22nd centuries, as the moment we took our first halting steps toward becoming an interstellar species. New Horizons' 13-minute flyby of Pluto and Starshot's potential 20-year journey to Proxima will be remembered as tentative experiments, primitive first attempts, the hesitant beginning of something far greater. But every journey begins with a single step. Every impossible mission starts with someone believing it can be done. The question isn't whether we'll reach the stars. The question is whether we'll start building the ladder to get there. The road to Pluto proved that impossible is just a challenge waiting for the right engineering. The road to Proxima will test whether we have the wisdom and determination to think in generations rather than years. If this exploration of humanity's reach toward the cosmic frontier inspired you, help spread the curiosity. Like this video, share it with someone who dreams of distant worlds, and subscribe to BrightBoundX for more deep dives into the missions that expand our understanding of the universe. Because the next impossible mission, it's already being planned, and you might be the engineer, scientist, or simply the informed citizen who helps make it real. Subscribe to BrightBoundX. Let's reach beyond boundaries together. The universe is waiting. Let's go see what's out there.